Lecture 7, Rolling Motion and Angular Momentum. Rolling motion and angular momentum is also the lecture where we see the real definition of torque. So an object that is translating and rotating gets both kinds of kinetic energy. So last time we introduced the concept of rotational kinetic energy, half I omega squared. And now if an object is both translating and rotating, then it has both of those. So you look at the velocity of the center of mass to get the kinetic translational energy, and to get the kinetic rotational energy, you use the moment of inertia about the center of mass multiplied by its angular velocity about its center of mass. If an object is specifically rolling, then it's a bit easier. You can relate these two velocities. You can say that the velocity is equal to the radius of maybe the object if it's rolling about its edge, or possibly an inner radius if this is like a spool rolling on a rail, multiplied by the angular velocity of the object. A force that's applied to an object, a displacement r away from its rotation axis, produces a torque. Tau is r cross f about that axis. Cross product is just a reminder that cross product between two vectors applies to two vectors in three-dimensional space. It's a way to multiply vectors besides the dot product. Dot product works for any dimension of vectors. Cross product is only for three-dimensional vectors. Now what you do is you write the vectors in component notation, and this vector cross this vector, you place them horizontally as row 2 and 3 of a matrix, where the first row is I, j, and k unit vectors. Then you take the determinant of that, which itself gives you I vector times 2 times 4 minus I times 3 times 0. J, go down and to the right, adding j times 3 times 2 minus down and to the left, subtracting j times 1 times 4. And k, down and to the right, adding k times 1 times 0, subtract down and to the left, k times 2 times 2. And there you have it. There's your cross product. You can also do determinant by cofactor expansion if you like. So you can say a times the determinant of this thing minus b, because on the checkerboard we've got positive, negative, positive, negative, positive, negative, etc. So minus b times what would be left, determinant of dfgi, plus c times the determinant of degh. Work that all out, and you can come up with this formula. Some people have this formula memorized. Good for them. That's great. If you feel like memorizing that, if you're going to be taking a lot of cross product, that's probably worth it. Personally, I just like to know how to find a determinant and then work this out manually every time I need it. I probably would have saved a bit of time by now if I just memorized this, but I prefer to go for understanding rather than just memorizing things. So understand why things work, and then you'll accidentally memorize them. Anyway, cross product has a magnitude of uv sine of the angle between u and v, as long as you pick a positive direction for sine of the angle between u and v. So if theta between u and v is larger than, or is negative, then you would get a negative result here, but that can't be true for the magnitude. So you just have to be careful about what angle you're using in this case. Again, cross product is only for 3 dimensions. U cross v is perpendicular to both u and v. And which one of the 2 possible directions is given by the right-hand rule. That's all the right-hand rule does. A lot of people will, when they're first learning about cross product, I know you guys would never do any of this, but a lot of first years that you may know would try to use the right-hand rule before they've realized which 2 possible vectors could be the result of a cross product. The trick about that is you know that it has to be perpendicular to both the vectors you started with. And so unless those 2 vectors are parallel or anti-parallel and the cross product is just 0 anyway, there's only 2 possible directions that the cross product could give you. You have to figure out what those directions are before you can start using the right-hand rule. In a standard right-handed coordinate system, then I cross j is k, and similarly j cross k is I, and k cross I is j. If you go backwards, then you'd get the opposite. So since u cross v is negative v cross u, that means j cross I is negative k, k cross j is negative I, and I cross k is negative j. Whenever you draw your axis, you can check that you've done a right-handed coordinate system by checking that I cross j is k, and that tells you you've done it right. Right. All right, so extra info. Torque is r cross f, the moment arm crossed with the force applied. This is the torque that force F applies about an axis, a distance r away from where the force is applied. Only the perpendicular component matters because the parallel component to the moment arm would give you 0 for the cross product, since the angle between those two vectors is 0. Here's a picture that you can get on Wikipedia, which demonstrates this a little bit. We've got a moment arm r, and we've got a force applied to this object. The force creates different torques about different points on the object. So about this point of where it's actually applied, it creates a torque of 0, but about this point, a displacement negative r away from the force application point. So that force application point is a displacement r away from this point we're finding the torque about. It creates a torque of r cross f. Using the right hand rule, you can see r crossed with f would be out of the page. The second thing we're going to talk about today is angular momentum. The angular momentum, given by the symbol L, of a particle about an axis is L equals r cross p, where r is the displacement of the object from that axis, and p is its linear momentum. Angular momentum is also equal to I omega, where I is the moment of inertia about the axis for which its angular velocity is omega. The net torque acting on an object is the rate of change of its angular momentum, and equivalently, torque is I alpha, because of the definition of alpha. So this is sort of our Newton's second law here. We can get a full list of linear and angular analogs. So the equivalent of force is torque, linear acceleration, angular acceleration, mass is like moment of inertia, velocity is angular velocity, displacement is position, so like linear position, angular position, linear momentum, angular momentum, and kinetic energy as well, related by similar formulas. Let's think about this calculation right here. To see where this comes from, you can consider substituting in alpha in terms of omega, and doing that below. We've got that tau is I alpha, but alpha is d omega by dt, and bringing the I inside that derivative as long as moment of inertia is constant, then we find that torque is also the required rate of change of angular momentum. Now looking at this animation to illustrate angular momentum, we've got the force applied in dark blue and the moment arm of the force application point about this axis in dark red here. So R is in dark red, force in dark blue, and it creates a linear momentum in time that increases while it's being applied and decreases there, increases the other direction. You can see that the torque is a constant while the constant force and constant R cross F is in play. But over the time of force, it increases linear momentum, and consequently, over the time of torque, it increases the angular momentum. Angular momentum and torque, you can see, are perpendicular to the plane that the moment arm and the force act in, and also the moment arm and the linear momentum act in. A pencil is balanced upright on a desk and allowed to fall over. As it rotates from vertical to horizontal, is its angular acceleration constant, increasing, or decreasing? Assume that the pencil doesn't slip as it's rotating. Well, let's look at some diagrams here. Initially, or at least a little bit after it started to rotate over, then we've got this R and this force. Force is the weight of the pencil applied at the center of mass. As you can see, once it's fallen a bit more, the angle between those two has started to open up, and we've got a larger torque. Therefore, the angular acceleration must be increasing as the pencil starts to fall over. Another astronaut problem, this time with spinning. Two astronauts are floating freely in space, joined by a rope of length 15 meters, and we know their masses, and one of them has a pack on, and they slowly revolve about their common center of mass at 1 RPM. After they gather the rope so that they're separated by only 10 meters, how long does it take to complete one revolution? All right, solving with variables. Let's say that so we can calculate the center of mass, and it's based on the distance apart of the two. So we've got the sum of the mass times the position. We've set the x-axis as 0 at the left there. Calculate the center of mass location and the moment of inertia about that center of mass, wherever it is. As they gather the rope, they decrease their moment of inertia and increase their angular velocity. Here's just a calculation of that. So rather than substitute the center of mass into the angular velocity, into the moment of inertia rather, ourselves, since we've got maple, we can just find x bar and then substitute that in. You'll notice that I used simplify here. If you find that the answer doesn't seem like the answer looks like it's a lot longer than it could be if you were to play around with it a little bit, it's usually a good idea to tell Maple explicitly to simplify things, and it'll try and eliminate variables that cross out and give you a nicer answer. Sometimes Maple can't do this because it doesn't realize that a variable is always positive, that you realize is always positive, so you have to use assumptions to help you along with simplify. Okay, another comment is that I called the moment of inertia MOI rather than I, like we were in our equations. That's because I is a reserved constant in Maple for square root of -1. From conservation of angular momentum, we have that the I omega is the same before and after they do this, which means that the omega final is the initial one times the ratio of the moments of inertia. And since we found out that the moment of inertia is equal to some constants times L squared, we can just substitute that in. We don't need to worry about the constants or any of the details of the mass or even the absolute value of the length and before and after, just the relative length change, square that. And so as we move from 15 to 10 meter separation, it must increase the speed by a factor of 15 over 10 squared, or 9 over 4. This means that it must decrease the period by the same factor. And so the new period of rotation, the time it takes for one revolution, is 4/9 of the previous one, which is 26.7 seconds. One more question for today. Rolling up a ramp. A thin ring of mass m rolls without slipping. At speed v0 is 2 meters per second along a level floor. There it is. And then up a ramp of vertical height 0.15 meters. What's the speed v of the ring when it reaches the top of the ramp? So a hint is, because they didn't ask you when the ring reaches the top of the ramp, that means that you can do this problem with energy. You don't really care about the time that it takes to get to the top of the ramp, and so energy is probably the easiest way to solve this. To do that, let's first relate the rolling motion to the linear motion because it's rolling, and the moment of inertia of this thin ring. All the mass is at the edge, so it's mr squared. The energy is the combination of three types. We've got linear kinetic, rotational kinetic, and gravitational potential energy. As the moment of inertia is mr squared, we can substitute that in, and we can substitute the angular velocity in terms of the linear velocity. You could also have put everything in terms of angular velocity. That's fine too. Either way, you find out that the energy is, you can kind of combine the two kinetic energy terms into one, and this is possible because for rolling, the linear motion is related to the angular motion. Whenever you have a rolling problem, you're going to want to relate those two. So energy is mv squared plus mgy, not half mv squared. This is interesting. The rolling means that an object rolling at you has, if all of the mass is at the edge, has twice as much kinetic energy as if it were just sliding at you on that frictionless surface. So watch out for steamrollers, very energetic. Energy is conserved, so E start is equal to E end, and E start is mv squared plus mgy, E end mv squared plus mgy, but we allow the heights and the velocities to change, which leads us to this equation. So then we found out that the final velocity is the root of the initial velocity squared minus gh. If you want the specific numbers, you can go ahead and sub those in. Let's consider the physics of this. So what's going on is, if the initial velocity were 0, then the final velocity is just 0. That makes sense. It can't get to any kind of a height. The higher the height that it gets to, the slower the velocity is going to be, and it kind of scales down like a square root term. That makes sense because the velocity increases the initial kinetic energy like it's square, but the height just decreases the energy linearly as it goes into gravity.